Hi, hello. Okay, last time, of course, we talked about automorphisms, and so I'm trying to sort of nail some of the intuition about these kinds of maps down. And so the check-in involves a geometry question. We're trying to talk about what does preservation of addition mean when you draw it in pictures. So let's get to it. I have two vectors in the plane 1, 2, and 3, 1. And I'm going to apply three different automorphisms. The map that multiplies all the vectors by 2, the map that rotates all the vectors by pi over 6, and the map that flips all the vectors, in this case about the line y equals x. Okay, so let's see how I do with this here. Probably not very well. So I'm looking at the two vectors. I'm looking at the two vectors 1, 2, and 3, 1. And w equals 3, 1. And drawing is definitely not a strength of mine, which is why I get the computer to draw as many pictures as I can get away with. But it's not awful either, so let's give it a whack here. You'd think I could do something. So I'll draw, and this is going to be the x-axis, and this is going to be the y-axis. I'll draw 1, 2, and I'll draw 3, 1, and I'll draw the parallelogram picture. Let's see, 1, 2, 1, 2, and 3, 1, 3, 1. And the parallelogram picture goes to what? 4, 3. 4, 3. There we go. Okay, so 4, 3. Okay, then question 1 says multiply everybody by 2. Look at the automorphism, the dilation map that multiplies everybody by 2. So for example, 2u is going to be 2, 4. And 2w, 2v, sorry about that. Why did I not put vector bars? 2v is going to be, 6, 2. And I'm going to have to draw a bigger picture. So instead of going to 4, I got to go here. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Okay, 2, 4. 2, 4. So 6, 2, 3, 6, 2, so. And when you add them together, 8, 6, 8, 6, so. So what this is telling me is this vector right here is d of u plus d of v, 8, 6. If you compare the two pictures, what it's telling me is that if you add d of u and d of v, you get the same answer as if you take the 4, 3 and double it. So double first and then add gives you the same answer as add first and then double. That's what preservation of addition tells you, of course, in this context. Okay, let's try rotating. I'm not gonna do the trigonometry to get the rotated vectors. I'm just gonna pretend that I rotated the vectors, and I actually don't even know whether they whether this one goes past the axis, but I'm gonna pretend it does, and then rotate that by pi over 6. I don't know, maybe so. And maybe the parallelogram diagram goes like so. Isn't it awful? I never did line to draw. There we go. So this is what happens if you rotate u and you rotate v, and you add. But it's also what happens if you add first and then rotate. Okay, so the geometry of preservation of addition is that you can add first and then rotate, or you can rotate first and then add. You'll get the same result. Okay, so for the third one, of course, going to do the flip. So what is the flip of u? Oh, U disappeared off the top of the page. What is the flip of U? Well, you take 1, 2 and flip it about the line y equals x. I think you get 2, 1. And the flip of V is you take 3, 1 and flip it about the line y equals x. You get 1, 3. See how I do with this drawing. Two, 1, 2, 1. 1, 3, 1, 3, versus 2 and 1, 1 and 3, so 3, 4. And again, the point of contrasting what's on the top to what's on the bottom is that you can think of this vector right here, the long side of the parallelogram, you can think of that vector either as the flip of U added to the flip of V, or it's also correct to thinking of it as the flip of U plus V. Okay, so preservation of addition somehow has something to say about the sort of before and after pictures here. These before and after pictures capture the whole f of U plus f of V equals f of U plus V. Okay, great. So let's see, what am I doing here? Oh yes, I have to pop that up, pop that down. There we go. Okay, got lost there for a second. Okay, so we're ready for what we're talking about for the day. The dimension characterizes isomorphism. We have a result that we want to talk about today. That how do you know when two vector spaces are isomorphic? And the answer will be if and only if they have the same dimension. So that's our big result for the day. The idea will be just this simple. If you have two vector spaces and you find a basis for the first, maybe it has 3 vectors. You find a basis for the second, maybe it has 3 vectors. Those will be isomorphic vector spaces. They are in some sense just like each other. And in fact, the isomorphism can be as simple as you take the two bases and associate them. That is to say, you take the first basis vector in the first space associated with the first basis vector in the second space. Second in the first space, second in the second space, third in the first space, third in the second space. So you associate the bases. So isomorphisms will associate all those things that are just like the things in the other space. And for example, they will associate bases. Okay, so let's go to it. So in order to prove the result that we need, I need a couple of technical things. In particular, I need this result. This is an interesting and sort of worth doing result all of its own. It's not obvious by any means, but I'm headed towards something bigger, so I'm going to give this one a little bit of short shrift. I am going to prove it, but you'll see I'm going to do it at sort of at a faster pace than the one that we're talking about today. Okay, so I have a space V and a space W, and there's an isomorphism from one to the other. I want to remember that an isomorphism is a correspondence. It's a one-to-one and onto map, and that any correspondence has an inverse function that takes you not from V to W, but instead from W to V, and the inverse function is also a correspondence. Okay, so that's a result about correspondences, about one-to-one and onto maps. And you can check the appendix if you need a little refresher on that. To finish, then, I have to show that the function f inverse preserves addition and preserves scale and multiplication. We saw the result last time that we can combine the two together, if we like, and just show that it preserves linear combinations of two vectors. So I'm going to take that. It's not much of a shortcut, but it's something of a shortcut, so I'm going to take it. So here it is. F inverse takes a linear combination and gives you, after a little bit of work, gives you a linear combination of the F inverses. Okay, so let's go through the steps. To get from F inverse of this linear combination, note that these are W's because F inverse starts in capital W. So to take F inverse of this linear combination, the first thing I did was rewrite W1 as F of V1 and W2 as F of V2. An isomorphism is a correspondence. So there's exactly, if you start with W1, there's exactly one V1. that F takes to W1, and there's exactly one V2 that F takes to W2, so I just wrote those in. F is an isomorphism, so it preserves linear combinations. Here we go. I rewrote C1 F of V1 plus C2 F of V2 as F of C1 V1 plus C2 V2. F and F inverse cancel each other. I got C1 V1 plus C2 V2, and I rewrote V1 as F inverse of W. So this is just some algebraic manipulation, one step to the other. Not trivial, but it is stuff that we've done before, not all that long ago, all the recent classes, in fact. So I'm going to pass over it a little bit. I am going to give an example, though. The statement that we just saw has something to say about isomorphisms that reinforces the kind of thing I've been talking about for a couple of videos now. In particular, in the last video, I talked about the line through the origin y equals 2x. I parameterized it this way. It's all multiples of 1, 2. And I said you can, if you like, one isomorphism you can make between this line through the origin y equals 2x and the real line, the vector space R1, is you can take t and associate it with t. So that, for example, 5, 10 is associated with 5. 2, 4 is associated with 2. And the inverse simply goes in the other direction. What's F inverse of 5? Why, it's 5, 10. What's F inverse of 2? Why, it's 2, 4. So you'll remember that when we first did introduction of isomorphism, the first couple of examples we did to try to build up some intuition had double-ended arrows. It said the things at the beginning and the things at the end match up with each other. And that's all we're saying here, is that the things in the beginning and the things in the end match up with each other. The 2 and the 2, 4 is a double-ended arrow between the two. They're associated together 1 to 1 and on to. Okay. So saying that everything matches up is saying that the two spaces somehow are just like each other, and so the universe of all vector spaces breaks up into cases. You have vector spaces that are just like each other, vector spaces that are just like each other, vector spaces that are just like each other. You break up into these communities of vector spaces where inside of a class, all the vector spaces are just like each other. Inside of a class, all the vector spaces are just like it. Inside the class, all the vector spaces are just like each other. And the point of the day today is to characterize those classes. If you look at a particular class, all the vector spaces that are just like R2, what's in there? And of course, I gave it away already. It's all the vector spaces that are two-dimensional. Vector spaces are isomorphic if and only if they have the same dimension. In the book's presentation, because each of the two halves is substantive, I broke it into two separate statements. And the two separate statements are, if spaces are isomorphic, then they have the same dimension. And if spaces have the same dimension, then they're isomorphic. So basically what we show is that the bases correspond. The proof of the first depends on showing that under an isomorphism, the image of a domain basis is a range basis. So the bases correspond. And then the second depends on giving an explicit isomorphism from an n-dimensional domain to Rn. So the book has the full proofs, and as I often do in these videos, instead of giving the full proof, I'm going to give an illustration that I hope helps a person get ready to read the full proof. Okay, so I'm going to look here at a two-dimensional space, the plane 2x minus y plus z equals 0 in R3. And based on the drawings that I drew at the beginning of this video, you can see why I got the computer to draw the plane for me. That area is the plane 2x minus y plus z equals 0, and those are two vectors in the plane, and based on this parameterization down here, the vectors are 1/2, 1, 0, and minus 1/2, 0, 1. This is minus 1/2, 0, 1. Can you see that it's a little bit back? Lies in the xz plane, and that's a height of 1. And so this must be 1/2, 1, 0. So this lies in the xy plane, and it's x equals 1/2, y equals 1. You can see why I got the computer to draw these things for me. I'm totally incompetent at it. So what I get then is that a basis for this plane is these two vectors, is the sequence consisting of those two vectors, 1/2, 1, 0, minus 1/2, 0, 1. I copied that to this slide just so that I wouldn't forget it. because the basis has two vectors, P is a two-dimensional space. Okay, and we talked last time about how the word two-dimensional matches up with our intuition of two-dimensional, that a plane is two-dimensional. All right, and then the second lemma is proof that this explanation is really supposed to be a warm-up for. It says that the following is an isomorphism. The map that associates each element in P, each member of the plane, with its representation with respect to this basis. Remember that the representation with respect to a basis is a too tall vector. So I'm going to associate each vector in the plane, each vector with the property that 2x minus y plus z equals 0, I'm going to associate with a too tall vector. And here's a typical example. I'll take 7/2, 3, and minus 4, and I'll associate it with 3 and minus 4. What's the association? Well, 7/2, 3 minus 4 is a member of the plane. So you can represent it with respect to this basis. So I did. I did the arithmetic. I'm not going to bother you with the arithmetic. So 1/2, 1, 0 times 3 minus 1/2, 0, 1 times minus 4. That's the 3. This 3 right here is this 3 right here. This minus 4 right here is this minus 4 right here. So I associate a member of the domain with its representation with respect to the fixed basis. I fix a basis, and I associate 7/2, 3 minus 4 gets associated with 3 and minus 4 because that's the representation of that vector with respect to that basis. Another example, same sort of stuff. I picked some crazy one at random from the plane, minus 17/4, 1/2, 9, some crazy thing that satisfies the property for the plane, and I represented it with respect to the basis, this basis up here. I got a 1/2 and a 9, and again, I'm not going to bother you with the Gauss's method to do that. I got a 1/2 and a 9, so I associate this vector v2 with 1/2, 9. So if you want to know who matches up in the domain space with who in R2, and the answer is just look at the coordinates of each vector in the domain space, write them as a too tall vector. That's who the association is with. The first lemma's proof shows that any isomorphism takes basis to basis. If you have a basis in the domain, then the image of that basis is a basis in W in the codomain in the range. So who's the basis here for the domain? 1/2, 1, 0 and minus 1/2, 0, 1. Who's the basis for the codomain for the range here? Well, this basis here is 1/2, 1, 0 gets associated with 0, 1, and this basis vector here, minus 1/2, 0, 1 gets associated with 0, 1. And obviously, of course, this makes a basis, namely the standard basis for R2. So the basis from the domain gets mapped over to the basis from the range. So we have an association, one to the other, of your coordinates with respect to the basis in the plane and your coordinates with respect to the basis in R2. Your coordinates with respect to the basis in P and your coordinates with respect to the basis in R2. And that's the association. That's the isomorphism. The corollary is that every finite dimensional vector space is isomorphic to one and only one of the Rn's, and that the reason for that is if you give me a finite dimensional vector space, it's got some number of elements in its basis. N. Every basis has the same number. Anyway, they all have n. This map that I just illustrated in the previous slide shows you how to associate members of the vector space you gave me with Rn. So every finite dimensional vector space, namely every n-dimensional vector space, is isomorphic to Rn. So when I had that picture earlier where I broke the universe of all vectors, finite dimensional vector spaces, up into separate parts, the parts that are all like each other, the parts that are all like each other, the parts that are all like each other, it turns out that in those classes, in those isomorphism classes, in those equivalence classes, in those parts, there's exactly one real vector space. So for example, all of the two-dimensional vector spaces are all together. They're in the same part, they're in the same equivalence class as R2. All of the three-dimensional vector spaces are all together. They're in the same equivalence class as R3. all the one-dimensional vectors, all the zero-dimensional vectors. Out here I didn't draw because I can't draw infinitely many cases, but out here all the 50-dimensional vector spaces, they're all together in the same equivalence class. They're all isomorphic to each other, and in particular they're all isomorphic to R50. So in some sense the Rn's represent their class. The technical jargon is the real spaces Rn form a set of canonical representative. Canonical means natural or obvious, or the thing that you would reach for. Okay? Okay. So big result, of course, didn't go through the proofs, but nonetheless tried to give some intuition about what's happening in the proofs. Basically, under isomorphism, everything corresponds. That includes bases, and it also includes representations with respect to the bases. So everything corresponds, everything of interest in a vector space corresponds the one to the other. I had a professor who used to say, under isomorphism, the second space is just the first space colored green. That is to say that there really isn't any, as far as vector spaces are concerned, differences between the two cases. The way I would characterize it is that any differences are typographic. If you have an isomorphism between 2x2 matrices and 4 tall vectors, it's just a different way of writing it. You could write it as a square, you could write it as up to down. It's just simply typographic. And he used to imagine that in one the numbers were blue and one the numbers were green, and that was the only difference. So vector space isomorphism tells you when things are alike, and it turns out we have a complete characterization of when things are alike. Things are alike when they have the same dimension. Okay, all right, very good. So next time we're going to start the next section where we take the map isomorphism that has it's a correspondence and it preserves linear combinations, and we're going to drop the correspondence part. Okay, very good.